Hello everyone, welcome to my class. Today I'm going to cover series solution of a linear differential equation. So in today's class, my class lecture is divided into two parts. First part, I will review some facts about power series, and in the second part, we actually use power series to solve the differential equations. Okay, so first let me start with notations and prerequisites. The first one, a power series in x minus a, so that is centered at a, is denoted and defined by the infinite series. Summation n goes to 0 to infinite cn times x minus a to the power n in the expanded form. This is this form. If a is 0, means the power series centered at origin is simply the infinite series of cn xn. Let me scroll down. Let's continue. A power series defines a function for x in the interval of convergence, which is denoted by fx equals to this power series, infinite series, summation n goes to 0 to infinite of cn times x minus a to the power n for all x coming from I. Derivative and integrations done term-wise. For example, for given power series f of x equals to the infinite sum n goes to 0 to infinite of cn times x minus a to the power n, the first derivative is, let's go here, cn is constant, keep as it is, then the x minus a to the power n, use your power rule to pull the n outside, then subtract 1 from n, so x minus a power n minus 1, then times by chain rule the derivative of inside, derivative of x is 1, a is constant 0, and our summation starts from 1 to infinite. Similarly, the second derivative, after all prime of x equals to, now summations, so here's n, now n minus 1, cn also constant, x minus a power n minus 2, you subtract 1 from n minus 1, and by chain rules, x derivative is 1, a derivative is 0, and summation starts from 2 to infinite. Similarly, the integrations of a power series is integration of fx dx left side, right side, I use again power rules. I'm here, so cn, so x minus a to the power n plus 1 divided by the new power n plus 1, and plus integration constant c, and the summation runs from n equals to 0 to infinite. Great, let me move on. Another property, identity property, if this power series equals to 0, so this implies cn equals 0 for all n. This does not mean that all cn's, means cn's are coefficients, this doesn't mean that all the coefficients cn's are 0. Another fact, for us, we consider analytic function as infinitely differentiable, so that means we can represent the function as in a power series. Now in Calc 2, if f is infinitely differentiable at a point, then it can be represented by either two ways, either Taylor series or Maclaurin series. The Taylor series has, the power series has center at A, and the Maclaurin series, the power series has center 0. So this is the form, so f of x equals to infinite sum and goes to 0 to infinite f nth derivative at a over n factorial of times x minus a to the power n. Keep in mind our n factorial, when n is 0, 0 factorial is 1. In part B, Maclaurin series, f of x equals to, and this is the infinite sum and goes to 0 to infinite, f nth derivative f at 0 over n factorial x to the power n. So we put a equals to 0. The arithmetic of power series The two power series can be combined through the operations of additions, multiplications, and divisions. Shifting summation index. For any integer k, the series is here starting from n0, but here it's starting from n0 minus k. So this means in general, in general term, replace n by n plus k and subtract k from the lower limit of the summations. For example, let's say example 7. Let's reindex for this given power series. Here n equals to 2 to infinite, n times n minus 1 cn f to the power n minus 2. Then in this one, let's replace our n equals to k plus 2, or k equals to n minus 2. K equals to n minus 2 here. Then now we're starting from k equals to 0. I put this index in k here. Okay, I can relevel later, put n equals to 0. Yeah, put k equals to n minus 2. Then your reindexing of the series here starting from 2. Now we bring from the summation starts from 0 here. Okay. So now that's the quick revisions. Now let's start solving the second order linear differential equations using series method. So the first quick recall, the second order linear homogeneous differential equation has a template in standard form, which is, the general form is here, which is a y double prime plus b y prime plus c y equals to 0. In the standard form, divide by non-zero a and simplify and relevel, it gives us y double prime plus px y prime plus qxy equals 0. This is the familiar expressions for us. Okay, now I do need one more definitions, that the ordinary point. A point and singular point. A point x0 is called an ordinary point if both the coefficient functions of px and qx are analytic at that point. That means the px and qx have Taylor series expansions around that point. Otherwise, x0 is called singular point. So let me state one theorem: existence of power series solution about an ordinary point. Let x0 be an ordinary point of a second order linear homogeneous differential equation. Then we can always find two linearly independent solutions in the form of a power series centered at that ordinary point. Y equals to the power series centered at x0. x0 is the ordinary point. Awesome. So let's move on. So, a quick note, the power series method is analogous to the method of undetermined coefficients. And for us, we pick ordinary point 0. Okay? So, let's start power series method. Here is the ideas, or here is a step you do need to remember. So we want to solve second order linear homogeneous differential equations. So y double prime plus pxy prime plus qxy equals to 0. So the step number first, assume our solutions as a power series centered at origin. And here I'm picking our ordinary point at 0. So y equals to summation n goes to 0 to infinite cn times xn. So the next, our goal is to find this coefficient cn. These are unknowns. So the next, substitute this power series or this y value into differential equations. Means put y equals to this power series here, take y first derivative and put in this term here, and take y second derivative and put here. Then find the recurrence relations. Recurrence relation means the relations among the coefficient of power series. then solve the recurrence relations for Cn's one by one for all I less than n in terms of C0 and C1, and write the general solution in this form: y equals to C0 times 1 solution y1x plus C1 times another solutions y2x. This y1 and y2 are the solutions. Let me recall that theorem here. It says it exists, so we don't need to worry about that, the existence part. It says we can always find two linearly independent solutions in the form of power series. So now we have y and y2. Let me scroll down again. Maybe here. Then write our general solutions as y equals to C0 times 1 solutions plus C1 times another solutions. And C0 and C1 are constant. They correspond to the initial conditions. If the question is initial value problems, we use initial conditions to compute C0 and C1. Great. So let me start the example now. Just a quick reminder here. So example 1 says find a, let me spell this way. Yeah, that's better. Find a series solution of the differential equations y double prime plus y equals to 0 about the ordinary point 0. By the way, quick comment here, all the real numbers are ordinary point here. We pick 0. So assume a series solution of the form y equals to this power series. We pick x0 equals to 0 here, where Cn's are constants to be determined. Then differentiate it term by term and substitute back into the differential equations. So y double prime, put it here, which is this one, n equals to 2 to infinite n times n minus 1 times Cn times x to the power n minus 2 plus y, just this one, equals to 0. Let me scroll down. So the next step, now we have to re-index here. Now set the indices. Here the summation starts from 2, here it starts from 0. So put k equals to n minus 2, k equals to n minus 2, then your summation starts from k, which is 0, it starts from 0, n is k plus 2, k plus 1, c k plus 2, x to the power k. We have to match this summation so that we can factor that summations out later. Okay, so now in this step, we factor the summation outside. K plus 2 times k plus 1 times ck plus 2 plus ck. We factor xk out, we factor the summation out. This equals to 0. Then using identity property, we stated in the revision part, so we can equate this coefficient equals to 0 for all k greater than or equals to 0. Then we got the recurrence relation ck plus 2 equals to minus ck over k plus 2 times k plus 1. So this type of relation between coefficient of power series is called a recurrence relations. Let me scroll down. Now to find the individual coefficients, assume C0 and C1 are given. Then following pattern emerges: either k is even or k is odd. So if k is even, so that means k equals to 2n. If k is odd, that means k is 2n plus 1. So that means I am computing on the left side the even case. That means C0, C2, C4, C6, C8, C10 and so on. And on the right side, I'm computing C1, C3, C5, C7, C9, etc. So then this is the relation. So let's compute, and we assume, by the way, C0 and C1 are given. So our answers, our coefficients are in terms of C0 and C1. Great. So what is our C2 then? Put k equals to 0. So C2 equals to minus C0 over, we put K0, so 2 times 1, 2 times 1, 2. This equals to minus C0 over 2 factorial. Let me, at the same time, the first one, let me compute the first odd also, so that I can show you this, the equation star and this computation here. So in the right side, first odd coefficient means C1 we already assumed. Now the next one is C3. Put K equals to 1. So C3 equals to, we put K equals to 1, so minus C1 over 3 times 2. So then here 3 times 2 equals to minus C1 over 3 factorial. Great. Now similarly, let me scroll down. Similarly, I am substituting value of K here on this equation star and computing other coefficients. Left side in terms of C0, right side in terms of C1. Okay, I hope this makes sense to you. Let me scroll down. So then in C4 gives us C0 over 4 factorial. C5 equals to C1 over 5 factorial. So one more time, let me remind you, left side all the coefficients in terms of C0, right side all the coefficients in terms of C1. We got these coefficients from that star equations. Okay, so then in general we have C2n equals to negative, this is, that's the pattern here, so that means let's see, C of 2n, these are the even coefficients, so either I get minus or plus or minus, so minus 1 power n, so it depends on n. So C0 is the fixed we got, and then in the denominator, if you have 4 here, 4 factorial, 6 here, 6 factorial, so that means for 2n factorial, right? Yeah, similarly, let's go to the right side. C2n plus 1, we are computing the odd coefficients. So again, either minus or plus, so minus 1 to the power n. C1 over what coefficients? If the third coefficient, 3 factorial, fifth coefficient, 5 factorial, seventh coefficient, 7 factorial, similarly, to n plus 1 the coefficients, 2n plus 1 coefficients divided by 2n plus 1 factorial. Great. So then let me summarize what we have so far. We assume our solution in the power series where Cn's, if it's an even case, we have this expression we got here. In the odd case, we found these expressions over here. So the general solutions of differential equations can be written as, then how you can write down, so yx equals to, this is the even case, so it's coming from here, so then I pull the C0 outside and I put this, I'm putting this guy's back here, so this guy is back here, so the two cases here, C0, and this is the coefficient xn plus C1 times the odd case 2n plus 1. Yeah, we got the solutions of given differential equations here. C0, this is one solution, y0 plus C1, another solution, y1. Sorry, y2, y1, y2. Great. Maybe here, let me show you the methods we did using undetermined coefficients. The same example. Let's solve quickly and let's see the comparison here. Okay. Solve. That is the questions given. Use undetermined coefficients method. First find the characteristic equations. M squared plus 1 equals to 0. Solve for m. This is the aside. I'm just showing you a comparison here. Okay. You don't need to do these methods here. So the characteristic equations. M squared plus 1 equals 0. This implies m equals to plus minus I. So that means we have a complex root. Then our general solution of the form is yx equals to, this is the formula. If I assume this is alpha plus minus I beta, then the solution is e to the alpha x times c1 cosine beta x plus c2 sine beta x. Here alpha is 0, beta is 1. So then our general solutions becomes yx equals to c1 cosine x plus c2 sine x, which is exactly we found here. Don't worry about this c0 and c1, these are the constant. c1 and c2 are constant here, but this is cosine x. This is the power series expansion of cosine x, and this is the power series expansion of sine x. So we found exactly the same answer. We are only learning here the alternative methods to solve the linear differential equations. That method is power series solution method. I hope it makes more sense for you now. Okay, now let's move on. Let's do other problems also. Let me scroll down. Example 2. That's better. Find two power series solutions of differential equations y double prime plus 2xy prime plus 2y equals to 0 about the ordinary point 0. So the same idea. Assume our solution is of the form this power series. Take the derivative, take the second derivatives. Next, substitute those values back on the given differential equations. Put y double prime here, put first derivatives here, and then y here, which gives me this one here. So 0 equals to, this is the y double prime plus 2xy prime plus 2y. So here is a small computations about shifting the index, or we call reindexing in the summations. So let's see here. Here summation first starts from 2. Here summation starts from 1, and some start from 0. At the same time, let's see the exponent term of x. Here's x to the n. Here we can multiply this x here, and it also becomes x to the n, right? You can cancel the 1, and now here x to the power n minus 2. So x to the n matches here. So that means later I can extract the x to the n outside, and I can fix these summations here because it's starting from 1, it's starting from 0. So if I compute n equals to 0, then the next term starts from n equals to 1. So I can rearrange this one, but here I need to bring this down to the power x to the power n, so that again I can factor x to the n from all of these three. So then let's shift the index. So put k equals to n minus 2. Here put k equals to n. Put k equals to n. I'm just fixing. I'm just taking all the indices starting from, as k. Okay, so then now k goes from 0 now. N minus 2 is 0. This n is k plus 2, k plus 1, ck plus 2. Now x to the power k. Great. Then plus. So here I multiply x inside and change n to k. And then here's, I didn't do anything. No, I did. I just switched from n to k index here. That's all. So now I have all xk. I can factor out, but I do need the summation has to be the same. So I fixed k equals to 1. Then the third one, I computed the first one, and I rewrite the index starting from 1, so that I can factor this k equals to 1 to infinite, that outside. And the same thing here. Starting from 0, I computed the 0th term, k equals 0, and then starting my summation from 1, so that I can factor outside the summation starting from 1. Hopefully it makes sense. So please make sure you understand this reindexing business here. Let me scroll down. Then what I did here, let's see. So then I computed k equals to 0. So k equals to 0. So 2c2 here, 2c2. And then the next term starts from 1. I wrote as it is here. K from 1 to infinity instead of 0. And k plus 2 the coefficients, k plus 1 coefficients, ck plus 2 coefficients, xk. Great. So now I didn't do anything. I just copy down here this part. And this part again I break down. K equals to 0, k equals to, and then next the summation k equals to 1 to infinite. So first put k equals 0 to c0, x0 is 1, and plus 2 times the series starting from 1. I hope it makes sense from going here, doing this reindexing business here, and going this step. So now in this step, now I can, out of those summations, I can factor the summations starting from k equals to 1 to infinite and xk outside. So I pull xk outside from this 3, and I pull this summation is starting from 1 outside. The what left? So let me start from the beginning. This is the 2c2, 2c0, summation starting from 1 to infinite outside, k plus 2, k plus 1, ck plus 2, xk, xk outside. From this one, I already pulled summation out, so what left? 2 times k ck left and 2 times ck left. Great. Because I'm looking for a recurrence relation, so that's why I'm just making the nice the relations between or among those coefficients here. Okay, so then I did this and I combine 2 out, ck out, so k plus 1 I wrote here, and then now here's, so thus now my left side is 0, by the way, my left side is 0 there. So then I use the identity property, this equals to 0, 2c2 plus 2c0 equals to 0, so this implies c2 in terms of c0, so c2 equals to minus c0, and this coefficient equals to 0, maybe here is better, yeah, the coefficients is 0, without summation, without xk, that's the identity property, correct? Yeah. And from this relation, ck plus 2 equals to negative 2 times ck over k plus 2. So k equals to 1 to 2. Awesome. Great. So now let's find, or let's compute term by term this ck's here. So to simplify our computations, since we assume c0 and c1 are given, right? But in this case, let's assume c0 is 0, c1 is non-zero, means 1, and in another one is c1 is 0 and c0 is not 0, which is 1. So hopefully, let me pause here and remind you, we have two solutions there, right? One, in the general form it goes c0 times one solutions plus c1 times another solutions, right? We can use c0 as an arbitrary, but here, just for the computation purpose, let's take c0 is 0 without loss of generality, and c1 is 1, and to find the one solutions, and to find another solutions, now just switch their values here. Take c1 is 0 and c2 is 1, and find the another solution. So that's the idea here. So now let me scroll down. Okay, so case A, where c0 is 0 and c1 is 1. So what is c2? Let's see. c2 is negative c0, so we put c0 0, so c2 is 0. Awesome. So c2 is 0. Oh, I cannot show you the both. Now what is c3? or I can maybe this one, C3, put k equals to 1. So minus 2, this is C1 over k plus 2, means k is 1, so 3, so minus 2 over 3 C1. And we know C1 is 1, the minus 2 third. Now similarly, I can show that star equation here. Similarly compute C4, C5, C6, C7. Then we got this solution. So y1 x equals to, what is my first question here? First question is C1, right? So C1 x1 plus C2 x squared plus C3 x3 plus C4 x4, C5 x to the power 5. But what are the coefficients here? Non-zero. So only C3 non-zero, C5 non-zero, C7 non-zero. So what do we have? We have C3, C5, C7, and so on. Awesome. Similarly, let's go to the right side. This time we are assuming our C2 is, C0 is 1 and C1 is 0. Then what is C2? C2 is, by the way, C2 is from here, minus C0 is 1, so C2 is minus 1 in this case, so this is different here, okay? Similarly C3, C4, C6, so here's C3, C5, C7 are 0, so that means we have all the even part there. So another solution is then y2x equals to 1 minus x squared plus 1 half x4 minus 1/6 x to the 6 plus dot dot dot. We found the two solutions. The question doesn't ask us find the general solution. The question asks us find the two solutions. Let me go back again and show you the questions here. Yeah, find the two power series solutions of given differential equations. So the another questions let's do. So by the way, this differential equation is with the constant coefficients here. Okay. So another one is, let's go down here to here. Now let's do another. Now this time let's find the, oh sorry, that's the variable coefficients. So sorry, let me go back again. Let me fix that. So it's not constant coefficient here. The first one was constant coefficient. The second one is a Cauchy-Euler type. Okay. So now let's go back. Example 3. So now this time let's find the general solutions of the differential equations. Initial value problem. So this is the second order linear differential equations. And then given initial conditions is y0 is 3, y prime 0 is 0. So using series terms up to and including x to the 6. So wow. So now what we do, we are finding these two solutions first, and then we combine. We put this one as a C0 times y1x plus C1 times y2x, and then to find the value of C0 and C1 we use these conditions, and we are only writing up to the term including x to the 6. Hopefully it makes sense to you here. So then let's start. Okay, assume the power series, this is the solutions, it is of the form of power series. Ordinary point is 0 here. Okay, so then next substitute that differential equations back to the given differential equation, this power series back to the differential equations here, and then do that reindexing business again, that what we did in the previous example. Exact the similar idea here. So then let me go here. Then here is summation. We can pull k equals to 1 to infinity outside, and we can pull x to the k outside. So inside part is the coefficient here, and this is 2 times c2, and then this 8 times c2, and then the next we factor out here, and then we use that identity property 2c2 plus 8c0 equals to 0. So c2 in terms of c0 is c2 equals to negative 4c0, and from this k plus 2 times k plus 1 times ck plus 2 minus 2 times k minus 4 ck equals to 0. Then we got the recurrence relation here. Ck plus 2 equals to 2 times k minus 4 times ck over k plus 2 k plus 1. I know a lot going on here, so I mean a lot of computations, the algebra here. Yeah, so now let's compute the values of ck's from equations 1 and 2. Again, the idea is we choose, we have two choices here, right? One options we pick c0 is 0, c1 is 1. And another option we choose c0 is 0. Oh no, c1 is 0 and c0 is 1. I'm just switching those guys here. Then as before, so compute these ci's here. So here's all the evens are zeros, here's all the odds are zeros. That's the computations. Then we end up here. Now we have the two solutions. So this up to this point, exactly similar to what we did in our previous example. Okay, so now we have two solutions here, y1x and y2x. Hence, let's combine these solutions for the general solution, right? That's how we write down the general solution. So our general solution is c1 times the c1 c2 are now different c1 c2. It's not that the previous c0 and c1. Okay, so any constant times the first solutions plus constant times the another solution. Just the linear combinations of those solutions. Awesome. Then the y and x we found here, y and x we found here. To find the values of the c1 and c2, use initial conditions. This is given to us. Then this gives us, using initial conditions, so put y0 equals to the given value, that means you are putting x equals to 0, and for the y prime you take the derivative of this one, and yeah, it's a polynomial. We can easily take the derivative using power rules. Okay, so then and use another initial condition and solve these two equations. So that gives us c2 is 3, c1 is 0. Then substitute back here. So then yx equals to, means our general solution is, so c1 is 0, so all gone. Wow. So only c2 is 3. So then 3 times 1, 3, minus 3 times minus 4 is minus 12 x square, plus 3 times 4 third is 4 times x to the 4, plus 3, this is 15 times, so 8 over 15 x to the power 6. And then our question asks us up to and including x to the power 6. So we stop there. We found. So let me make one more final comment here. There is absolutely no way to know a priori how many terms you need to compute before obtaining the required non-zero terms here. We don't know in the beginning, right? Some terms are zeros, some terms are not zeros. So for example here, in this case, all evens are zeros. In this case, odds are zeros. And again, when you combine, then what's the c1 and c2? We don't know these values. Might be c2 0, that means we are only answering from this part. Or c1 zeros, we are answering from this part. So we don't know a priori how many terms you need to compute before obtaining the required non-zero term, that what we said in the questions here. Let me show you the questions here. Here. Okay, great. Hopefully it makes sense to you, this power series methods. So we finish this chapter 6, and at the same time we finish the differential equations for this semester. Thank you.